Hello, everybody, and welcome to another wonderful day of chemistry. So previously, we've talked about how light can act both as a particle and as a wave. However, it turns out as quantum mechanics went along, they discovered that it isn't just light that does this. It turns out everything does this. All matter behaves as both a particle and a wave. And one of the most true expressions of this has been called the Heisenberg uncertainty principle, which you've probably heard before in pop culture, is this idea you can't know exactly where something is if you know how fast it's moving. So let's go ahead and look into what this actually means. So first important feature of quantum mechanics is that all objects are both particles and waves. Most of the time, what happens is that the wavelength's just a little too small to notice. So let's say I've got an electron moving through space. So what I really have is I have this series of waves that is put in a packet. So this is often called a wave packet, where the electron can be anywhere in this space, but it's more likely to be some places than it is others. So it's much more likely to be here towards the middle with high probabilities, but it also has the occasional nodes that cut through the center, where it's most likely not going to be located. And it's this awkward behavior of essentially high and low probability locations of the electrons that often causes some difficulty. But a good way to think about it is that an electron moves around a lot like a dust bunny. You generally know where the dust bunny is. However, when you start looking a little closer, you're going to find that there's certain places it just isn't, and certain places that there's a lot more dust bunny than in other places. But trying to pin down exactly where in space it is gets a little harder the closer you look. And that's more or less what happens with most objects. And a good way to describe this is using what's called the de Broglie wavelength. So it looks at the specific wavelength of an object. So the wavelength of the object is going to be dependent on three factors. The first is our good old Planck's constant. The second is going to be the mass of the object, and the third is the velocity. Well, Planck's constant is a constant, so that's actually pretty easy to handle. But let's go ahead and look at mass. So what we find is that if I've got a small mass, I'm going to have a large wavelength. If I have a large mass, I'm going to have a small wavelength. So practically speaking, what this means is that if I have a large macroscopic object, the wavelength is far too small to really notice. And this is the reason why in the everyday world, we don't think about objects behaving like waves. And honestly, even by the time you get down to a proton or an atom, you still don't see much wave-like behavior. It practically takes getting to the electronic level before this wavelength becomes very noticeable. Also, what we tend to find is that there is going to be a velocity dependence. If I've got a fast moving particle, I'm going to have a very low wavelength. If I have a very slow moving particle, I'm going to have a very big wavelength. But it is worth noting that the speed term isn't nearly on the same scale as the mass term. And we'll go ahead and take a quick look at this. So let's go ahead and take a look at about as small of an object as we can, an electron traveling at a relatively fast speed. So about 1/10 the speed of light. So this is about as fast as we usually expect objects to go. And even at this fast speed, which should help lower the de Broglie wavelength, we're going to still see some fun features. So here's our mass, here's our speed, and just in case you forgot, Planck's constant, which can be put in one of two terms, either joule seconds, as I provided to you earlier, or if you want to watch your units, joule is the same as a kilogram meter squared per second squared. So this means that my overall units is going to be kilograms meters squared per second, if you want to watch your units. So we go ahead and plug in our plug into our de Broglie equation. So we have our Planck's constant divided by the mass times our speed. And it turns out that the wavelength of this object is about 2.43 times 10 to the negative 11th meters, or as I like to put it, 24.3 picometers. So this looks like a really small distance. So why do I really care? except for it's important to note that we're talking about a really small object. This is an electron. And 24.3 picometers is actually really big on an atomic scale. This is about half of the radii of an n=1 orbit. So if I have an electron in its first energy orbit, it's spending most of its time spread out over this kind of range. And it's worth noting that this is at a much faster speed than I typically expect an electron. So what we tend to find is that one of the reasons why we have to worry about quantum mechanics when talking about electrons is because the electron is literally going to be smeared over the entirety of the atom. So this wavelength is pretty comparable to the size of an atom. And so it's important to think about electrons not as being discretely located, discrete particles rotating around a nucleus, but instead about a particle that's moving so fast that it really literally ends up showing up at multiple places at once. And that's really what we're seeing with atomic physics. And one of the things of why we have to acknowledge the presence of quantum mechanics. However, one of the things that is very important is because matter has this wavelength, and especially at an atomic scale, it's pretty big. We don't always know exactly where it is or where it's going at any given point in time because it's a wave, and you don't always know position and movement of a wave. And it turns out that this can be expressed mathematically via what's called the Heisenberg uncertainty principle. So what it says is that the product of the uncertainty of position times the uncertainty in momentum has to be greater than or equal to the Planck's constant divided by 4 pi. And practically what ends up happening is that the more I know about the position, the less I know about the momentum, and vice versa. However, we often don't think about things in terms of momenta. Much more likely, we're talking about velocity. And you can actually express the uncertainty in momentum based on the uncertainty in velocity. So momentum can be given as mass times velocity. So the uncertainty in momentum can be given as mass times the uncertainty in velocity. So let's go ahead and take these two equations and apply it to something actually at the macroscopic scale and see why most of the time we don't have to worry about the Heisenberg uncertainty principle. So let's say I weigh about 60 kilograms, so 150-ish pounds, and we know that I am moving less than 1 millimeter per second. Again, this actually is probably pretty realistic. So if I'm holding my breath, my chest is probably vibrating less than 1 millimeter per second. So given these two constraints, what's going to be the uncertainty in my position? So what's the maximum I can know how close I am? So again, we can take uncertainty in momentum is equal times mass times the uncertainty in velocity. So I know my uncertainty in my velocity is at least 1 millimeter per second, or 10 to the negative third meters per second times 60 kilograms, and there's my velocity. 60 times 10 to the negative third kilograms meters per second. Then I can go ahead and plug this into my equation to get the uncertainty in position. So I've got Planck's constant up top, 4 times pi times my uncertainty in momentum. And my uncertainty in my position is going to be at least, but more likely greater than about 5 times 10 to the negative 31 meters. This is really small. And even if I assume that I have an uncertainty in my momentum greater than this, it's not going to be that much greater. So I'm not going to have that much more precision in my velocity, or much less precision in my position. So this is the reason why when we're talking about real sized objects, we know their position really well. But as this mass gets smaller and smaller and smaller, well, then it gets a little bit more messy. So you can go ahead and repeat this process for an electron. And let's say, again, I'm assuming its uncertainty in its speed is about 1/100th or 0.01 the speed of light. So I know that it's traveling somewhere around, I know it's traveling up to 1% of the speed of light, which is actually pretty realistic for an electron. So if I know it's traveling somewhere less than 1% of the speed of light, its uncertainty in this location is going to be about 23 picometers, which again, as I said previously, is about the size of the first electron in a nucleus. So really what I'm seeing is that this is another way of saying that electron is spread all across the middle of an atom. And this really helps show that messy behavior of electrons. They're not in one given location at any certain time. They're constantly wandering around the atom at fairly high speeds, sometimes more, sometimes less, sometimes near, sometimes far. It's hard to pin them down any more than this. The more I know about the position, the less I'm going to know about its speed. The more I know about its speed, the less I'm going to know about its position. So in reality, this is that tricky part about describing electrons, is that they are inherently dispersed waves. They are a dust bunny wandering around a nuclei. So we're going to try and develop a better way of talking about particles that act like waves next time, where we're going to be specifically trying to contain our little wave-like particle to a nice, healthy box, and then seeing if we can expand that to a more relevant atomic system. Until then, take care.